Okay, here is the final video for Taylor-Maclaurin series, at least the first part of that assignment. So this time we're going to look at developing a Maclaurin series for the general binomial function. So 1 plus x to some kind of power. So for any kind of power, and then we'll do it with one specific example. And then we're going to determine its radius of convergence as well, or at least we'll talk about it. Okay, so same strategy, we're going to apply our brute force approach and take some derivatives. So the first derivative, you bring down the k minus 1. Second derivative, bring down the k minus 1, k still there, k minus 2, etc., etc. So you can come up with the nth derivative. It looks like it's kind of like a factorial thing down here, but not quite. So you have kind of a factorial part here. It goes, if it's the nth derivative, let's just see, the third derivative went to 2, second derivative went to 1 right here. So the nth derivative is going to go to k minus n plus 1. So k minus n plus 1. You see that? And then this is going to be k minus n because 3 is 3, 2 is 2. Can you see the pattern? Okay, then they said they wanted a Maclaurin series, so we'll plug in 0 for all those. So this part is just going to become 1 to some power, so you can see why that 1 plus x thing is gone from all these. Because 1 to any power is 1. Okay, so here is the expanded form of the generalized binomial Maclaurin series. Okay, trying to write it like this is a little bit tough. But I mean, it's basically the same thing. It's just going from 0 to infinity, and then you're going to take this piece from right here and plop it right there. Okay, so that's what it looks like in that form. Anyway, they're saying that if you do the ratio test, and we'll do part of the ratio test on one of these. I don't really think it's necessary, though, to show it for the whole thing, so you should be able to do that by now. So if we take the ratio test, you'd get that it converges to 1, so the radius of convergence is 1. So the generalized binomial Maclaurin series has an interval of convergence of negative 1 to 1. Okay, so let's go back down here and look at that. Okay, so now let's use it on a specific problem. So can we find a power series for this guy? So I think the answer is yes. We can use that generalized binomial series that we just developed, and then just plug in k equals 1/3, because cube root is k equals 1/3, right? So plug in k equals 1/3, so you get a third right there. A third minus 1 is 2/3. What's a third times 2/3? That's 2 over 3 squared. There's their 2 over 3 squared. And then this part is just from the generalized Taylor series, right? Remember, that's true for any Taylor series. If you ever get confused, just go back and look at the form of any Taylor series, and you'll see that there's always a 2 factorial. There's always x squared with the c thing right there. And we don't have to worry about that because we did like a Maclaurin series in that one, right? C was 0. Anyway, I like to go back and look at that sometimes. Okay. So this is what you get. So they're saying it converges from negative 1 to 1. Notice, though, they said that it does converge at the endpoint. So that's implying that they checked the endpoints. So I thought instead of just doing the entire ratio test, let's just check one of those endpoints and then talk about it. So maybe we'll extend the page slightly here and do some work on the bottom. So let's see, if we're going to check one of those endpoints, aren't we going to have to plug in? So we're going to have the series from n equals 0 to infinity. And what does that look like? If we go for 1/3, it's going to be 1/3. So I'm just going back up to right here and plugging in. Okay? So it's going to be 1/3, 1/3 minus 1, 1/3 minus n, blah, blah, blah. Okay, so it's going to be 1/3, then 1/3 minus 1, then 1/3 minus 2, and since it's a series, it has to be carried out. And then at the end, we had 1/3 minus n plus 1, x to the n, and then it was all over n factorial, wasn't it? Let's go back and look. Yes, n factorial. Okay. So if we're going to do check one of the endpoints, let's just check 1. Let's check this endpoint. We know it converges on the open interval -1 to 1. Remember, we're just checking to see if it converges at the endpoints, just like we do for any other power series. So we plug in x equals 1. So this guy is going to go right here, right? So the question is, does that converge or diverge? And I think we need to do the ratio test. So this is what we did back up here when they decided that it converged on the interval -1 to 1. What they did here is they applied the ratio test. So I'm going to have to apply the ratio test even to check just the endpoints. So I'll do it with 1, and I'll leave the other one up to you. So the limit as n goes to infinity, and this is going to be crazy, I think. So let's see. So we're going to have this guy to the n plus 1, right? So it's going to be 1/3, 1/3 minus 1, dot, dot, dot. N plus 1 goes on top, right? So it'd be 1/3 minus n plus 2, I think, yes. And then we'd have n plus 1 factorial right here. And then divide by just that thing to the n, so we'll flip it, do reciprocal, and put this guy up here. And then down here we're going to have 1/3, 1/3 minus 1, dot, 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 all the way to the end. And the last thing for the here is going to be 1/3 minus n plus 1. Extend that page. So that's going to be equal to the limit of, let's see, what cancels here. So this is going to go to just n plus 1. I think all these terms are going to go away, aren't they, except for that part up there. So just that part's going to be left. So we'll have 1/3 minus n plus 2 over n plus 1. We take a limit of that. The only thing that really matters is the n, so the limit is going to go to -1, isn't it? A -1 is always less than 1, so that converges. Yay! So we showed that it converges at 1. I'll leave it to you. You could put -1 in there and show that that converges. The same kind of way. I obviously don't want to write it out again right here with my mouse. But don't we have a theorem back from previously in the chapter that says if the series of an absolute value converges, if that converges, then the series also converges back around absolute convergence. So I think that if we took the absolute value and just put our -1 in here, then that would be this guy, which obviously converges. So I think we would know that that converges by that theorem as well. Remember that if you have a series a sub n that converges, that does not imply that the series of absolute values converges. That's definitely not true. If you look at like the harmonic or some simple examples, you'll see that that's not true. But anyway, I think that is a nice way to end this lesson. So next time we'll look at all the basic, well-known Taylor series or Maclaurin series expressions for the basic elementary functions, and we'll just move them around, and that'll probably be a little bit easier. So see you then.